Welcome to today's Explainer. We're diving straight into a massive, literal paradigm-shifting breakthrough in the world of advanced computing. For years, we've all kind of thought of the next generation of computing as something locked away in these freezing, multi-million-dollar underground facilities, right? But what if the key to unlocking the future isn't a massive cooling tower, but a diamond? Today, we're unpacking a technological leap that takes quantum mechanics totally out of the science fiction realm and potentially puts it right into your home or office. Section 1. A desktop quantum computer, leaving the lab behind. Okay, so let's dive right into this. Can a quantum computer run on a regular wall outlet? I know. Traditionally, asking that sounds completely absurd. If you know anything about the current state of quantum computing, you're probably picturing those giant chandelier-looking machines encased in gold, operating at temperatures literally colder than deep space, and requiring massive amounts of specialized power. The idea of just grabbing a plug and sticking it into a standard wall socket? It seems downright impossible. Well, get this. A German startup called Saxon Q has achieved exactly that. They've built the very first diamond-based quantum system with more than 10 qubits. And the absolutely mind-blowing part? It runs entirely at room temperature, and yes, it plugs directly into a regular wall outlet. They've completely bypassed the need for extreme cold by leveraging the incredibly unique properties of diamonds. Section 2. Bits versus qubits. The power of both. To really grasp the massive stakes of this breakthrough, just think about a regular computer bit. Everything your current laptop or smartphone does is based on the strict binary limitation. It's either a 1 or a 0. It's a simple light switch, on or off. But a qubit? It doesn't have to choose. Because of the totally bizarre rules of quantum mechanics, a qubit can be both a 1 and a 0 at the exact same time. So why does that matter? The crucial point is what that both-at-once trait actually allows us to do. Because a qubit isn't locked into just one single state, quantum computers can check thousands of combinations simultaneously. Instead of trying one path, hitting a dead end, backing up, and trying another path, which is exactly what a regular bit does, this system tests every single path, all in a single calculation. It makes quantum computing exponentially more powerful. We're talking about solving complex problems in seconds that would literally take traditional computers thousands of years. Section 3. The diamond defect. Flaws that function. So how on earth is Saxon Q creating these vital qubits inside a diamond at room temperature? When we think of a diamond, we usually picture a perfect, flawless crystal structure where every single atom is carbon. But occasionally, an imperfection naturally occurs. A nitrogen atom sneaks in, takes a carbon atom's place, and it just so happens to sit right next to an empty gap in the diamond lattice. This specific flaw, this exact microscopic imperfection, is Saxon Q's secret sauce. Because of that empty gap, the trapped nitrogen has an electron that's just left sort of hanging there. And that isolated electron acts incredibly uniquely. It basically behaves just like a tiny magnet trapped inside the diamond crystal. Imagine a microscopic compass needle floating inside an impenetrable microscopic vault. Of course, a tiny magnet is totally useless if you can't control it, right? So how do scientists manipulate a single electron trapped inside a diamond? It's actually a precise two-step mechanical process. Step 1, they fire a laser at it. This laser energy effectively resets the electron to a known starting position. Then, step 2, they use carefully timed microwave pulses to steer it from there. By resetting it with light and steering it with microwaves, that single trapped electron becomes the qubit. Section 4, the sulfur solution, forcing the defect. Now, all of this sounds like an incredibly elegant solution, but here is the massive roadblock they hit. What happens when those defects refuse to form where you actually want them? Getting these precise atomic defects, a nitrogen atom sitting perfectly right next to an empty gap, to appear in the exact right spots on a diamond chip almost never works naturally. And if you can't place the defects reliably, well, you can't build a computer chip out of them. So Saxon Q's brilliant workaround? They introduced a completely new element into the mix. They began artificially implanting sulfur atoms into the diamond alongside the nitrogen. It is an incredibly clever bit of microscopic engineering. Let's look at the chemistry of why this fix actually works. When those sulfur atoms are implanted, they naturally donate a spare electron to their environment. That extra electron stabilizes the whole system. It essentially forces far more of those nitrogen defects into a usable state. By adding sulfur, they literally cracked the code on how to manufacture these diamond qubits reliably and in high enough numbers to actually build a working machine. Section 5.
Goodbye, cryogenics. Hello, desktops. The new reality.
With that atomic manufacturing hurdle cleared, let's zoom back out to the macro level. Because the qubits are so heavily protected within the tough crystal lattice of the diamond, this entire machine is unlike anything the quantum world has ever seen. The full machine literally slides into a standard server rack. No cryogenics required, zero massive cooling infrastructure. It's practical, it's physically compact, and it operates at regular old room temperature, all thanks to the diamond. 99.98%. Just think about that number for a second. In the world of quantum computing, creating the qubits is really only half the battle. The other half is keeping them stable enough to actually perform calculations without throwing a bunch of errors. Saxon Q reports a 99.98% accuracy on single qubit operations using this diamond system. And to anchor that incredibly high percentage to reality for you, that level of accuracy is directly comparable to the quantum computing results we're seeing from IBM. Let that sink in. We're talking about a startup matching the performance metrics of one of the biggest, most well-funded tech giants in the entire world. And they're doing it without any of the massive chilling equipment that IBM relies on. If this holds up, it completely changes the trajectory of advanced technology as we know it. Which leaves us with this final, crucial thought for today's explainer. If quantum computers no longer require a massive freezing lab, and they can literally just sit right under your desk plugged into a standard wall outlet, what will you compute? Thank you so much for joining me today. Keep learning, keep exploring, and I'll see you next time.